Form of a carbonyl compound essentially makes the alpha carbon of a ketone or an aldehyde nucleophilic at that position. We can see this by drawing another resonance form of the enol tautomer. So if we take a lone pair from the OH of the enol and push electrons towards this alpha carbon, we will find this other resonance structure which has a negative charge on that alpha carbon. That means that enols are nucleophilic or electron rich at that carbon, and so they can react with different electrophiles that would add to that carbon. Removing this hydrogen after the addition of an electrophile to the alpha carbon will give you a ketone that has a substituent here. Here is a general mechanism of how ketones and aldehydes will add different electrophiles to the alpha position through the enol form or the enol tautomer. If we start off with a ketone or an aldehyde and we add acid catalyst, the carbonyl will be protonated. So the carbonyl will go after a hydrogen from, let's say, HCl to give us this protonated intermediate. And then this enol would attack an electrophile and do a substitution at the alpha carbon. Note in that process, we are reforming the carbonyl. So we have a protonated carbonyl here plus an electrophile. We can draw another resonance form by breaking the double bond of the carbonyl, pushing electrons towards the oxygen to now have a positive charge on the carbon rather than on the oxygen. And then if base removes this proton, reforms the carbonyl, we will go to a ketone product that has a substituent at the alpha position. So overall, this reaction will replace an alpha hydrogen with an electrophile. So these types of reactions, which we're going to look at in a moment, are called alpha substitution reactions. Note that the first half of this mechanism is just simply an acid-catalyzed conversion of a keto form into an enol, and then that enol will react with an electrophile to add a substituent at the alpha position of the carbonyl. Aldehydes and ketones will react with Cl2, Br2, or I2 under acidic conditions to replace a alpha hydrogen with a halogen. As an example, acetophenone, when mixed with acetic acid, which would be our acid catalyst, and one equivalent of Br2, will lead to replacing one of these three alpha hydrogens with a bromine. Note that the left side has no alpha hydrogens, and so no substitution will occur on that side. If we have an unsymmetrical ketone, the alpha halogenation can occur at one of two locations, and generally, we will get the substitution at the more substituted side of the ketone, since that is where the more substituted enol will form, and more substituted enols are generally more stable than less substituted enols. This is similar to what we see with alkenes. So you can think of an enol similar to an alkene. And so using this example here, we have this unsymmetrical ketone. It will prefer to form an enol on the left side of the molecule. So here is the enol form that would form. We would find a double bond on the left side. We would find an OH here where the carbonyl used to be. And we'll have a methyl group here as well. So the molecule prefers to form this enol rather than the less substituted enol, which would look something like this. So same cyclopentane. The double bond of the enol would be towards the right side in the less substituted enol. We still have the methyl group here. So this enol is less favored since the double bond is less substituted compared to the double bond on this one. And so the reaction will occur through the more substituted enol, and therefore the substitution of the halogen will occur on the left side of this ketone. So look at the acid-catalyzed alpha halogenation of ketones and aldehydes. It starts off with a ketone or an aldehyde being protonated by acid, either acetic acid or HBr, which results from the mixing of acetic acid and bromine. The carbonyl gets protonated. That gives us this protonated carbonyl, which then reacts with base. The base will remove the acidic alpha hydrogen, form a double bond here, and then break the carbonyl. That leads us to this enol. Notice that these first two steps are essentially the conversion of a keto tautomer into an enol tautomer. The enol tautomer will then react with Br2, where a substitution occurs now at the alpha carbon. We can draw two resonance forms of this intermediate. So if we break the carbonyl, we can place a positive charge on the carbon rather than on oxygen. Base will then remove the proton on this oxygen, and we can also use the same base to remove the proton on this other resonance form. Either way, we're going to go to a product that has a carbonyl, and we have replaced one of the alpha hydrogens with a halogen. Treating alpha haloketones with base yields an alpha beta unsaturated ketone. An example shown here with an aldehyde. If we do an alpha halogenation under acidic conditions, it produces the typical alpha halogenated product, which if we add pyridine and generally we heat it, we can do an elimination reaction by removing this proton, leading to a double bond here and elimination of the halogen. As a result, we get an alpha beta unsaturated aldehyde. Note that this is called an alpha beta unsaturated aldehyde since the alpha carbon and the beta carbon contain a double bond. In the next example, we have a ketone that is unsymmetrical. If we add Br2 in acetic acid, we can do an alpha halogenation of the more substituted carbon. And so we get a bromine on this carbon. Treatment with pyridine and heating leads to a elimination reaction that produces an alpha beta unsaturated ketone. Let's now review the reactions from this section by doing this problem. We want to prepare a 1-pentene 3-one compound from 3-pentanone. 1-pentene 3-one from 3-pentanone, we would do an alpha halogenation under acidic conditions. So we could add one equivalent of Br2 and acetic acid to replace one of the alpha hydrogens with bromine, and then treatment of this product with pyridine and heating will result in an elimination reaction that leads to a double bond between the alpha carbon and the beta carbon as seen in 1-pentene 3-one.